Hey everybody, happy Memorial Day Monday. Not supposed to see that calculator. There we go. Alright. I'll see you guys tomorrow. Tomorrow will be Tuesday. Tuesday we'll review. We'll go over all these questions again from this packet. We'll go over any questions you have from the homework packet too. You gotta be doing that. And hopefully by Wednesday you'll be all good, because Wednesday is your quiz. Looking here, here's a list of all your objectives: plot points, convert points, give me multiple points that represent the same location, convert equations back and forth, rectangular to polar, graph simple polar equations like r equals a number, theta equals a number, but also be able to graph more complicated ones like circles, limacons, cardioids, and roses. Yeah, that's about it. Except, of course, for this bullet, solve systems. And graph together in the same coordinate plane. And mark points of intersection as solutions or common points. So we'll hit all of that. There's an example of all of that in this packet, so we'll get to it, and hopefully you won't have too many questions, but again, if you do, Tuesday is a review day, so you'll hit me with questions on Tuesday. Alright, looks like we're plotting points first, which I think everybody's got down pat. If you understand it, then just move on. But to plot the point 3, 0, you just go out a distance of 3, and then you don't rotate at all, so you just get a point right there, and that will be point A for us. Point B wants us to go out a distance of 2 and then rotate through an angle of negative pi over 4. So that'll plop us right there. That'll be point B. Point C, I don't know what's going on with point C. What was that supposed to be? I don't know. That's whack. So let's say negative 3, 1. Let's, I don't know, pretend that that means 1 radian or something. 1 radian, you guys should know. Isn't that like 58 degrees, I think is what it is? I don't care. This shouldn't say 1. Like, that's foolish. So let's make up something else. Let's just make it pi over 3. Alright, so pi over 3, and with a radius of negative 3, means you probably want to do the rotation first. And so pi over 3 would put you here on a 60-degree angle. But the fact that it's a negative radius means that instead of sort of projecting along a pi over 3 radian angle, you project in the exact opposite direction. Hopefully you guys remember. So we'll end up going down this way 1, 2, 3 units and getting a point called C. And then finally we've got this guy. So negative 19 pi over 12, where the heck is that? That's 12 pi over 12 plus another 7 pi over 12. Yeah, sure. Okay. So negative 12 pi over 12 would have us go blah, blah, blah. That's a half turn. Then another 7 pi over 12. Well, you can see it right there. That's apparently 90 plus one of these little sectors. So if I'm coming in the negative direction, I'm just going to go 90 and then one more sector. So 5 pi over 12. That should be the angle we're looking at when we think about negative 19 pi over 12. Then of course it says go 5 units, and we know that we will go 5 units the opposite way. So we'll go 1, 2, 3, 4, 5. And we'll get a point here called D. So there's our 4 points plotted on the coordinate plane. Maybe more importantly is down here where it says express each of these points 3 other ways. So for part A, basically what you want to do is you want to give me one, I think it said this in the list, right? Yeah, You want to give me something that's plus plus, something that's plus minus, something that's minus plus, something that's minus minus. That's a good sort of benchmark for how to do this. So the given point, with 0, I guess you're up a creek. Not really. So instead of 0, we could of course just say 360. And that would be technically a different point. Although if we're sticking to radians, you would of course say 2 pi instead. You could always change the radius to be -3 and then give the opposite pointing angle, which would be pi. You could go with -3 and then the opposite, that angle you could give -pi instead, and that would work. So what am I missing? Positive radius with a negative angle. I mean, we would just go 3 and a -2 pi. That would be the same diff. So there you go. There's three different. I guess I gave you 4. There's 4 different ways to do A. So for B, we've got 2 comma -4 or 2 comma -pi/4. So another option for B then would be keep this positive, but instead of -pi/4, just go positive 7 pi/4. So there's the positive option. If we go with -2 as a radius, then you can see that the sort of opposite angle we would want is 3 pi/4, so you'll use that. And of course our negative option would be -2. And our negative angle would come around to 3 pi/4. That would be 5 pi/4. -5 pi/4. So all of those ordered pairs should have the exact same location in the plane as that one. Next, our modified part C. So it's already negative-positive, so let's do negative-negative. Pi/3 negative would be negative, what is that, 5 pi/3? We could make a +3. Yeah, and if you want to hit C, then you'd have to rotate onto 4 pi/3. There's your positive. And your positive-negative would be a positive radius of 3, but a negative rotation angle of 2 pi/3. And then finally for D, we've got our negative, so let's do a negative-positive. So without changing the radius, the positive angle that would rotate us here, well, you can see it printed right there, 17 pi/12. If we made the radius positive, oh, that's not right. Sorry, that's wrong. If we want to be using a negative radius, then we have to use the opposite angle. We want 5 pi/12 here. And of course I'm figuring out that now because as I change the radius to +5, that's when we want the 17 pi/12. And I could change negative. No, keep the radius positive, sorry. And the negative rotation angle that we want would be 7 pi/12. So we had a negative, now we've got a negative-positive, this was a positive, this is a positive-negative. Yep, that's everything. Alright, there you go. You should be pretty good with just plain old coordinates now. To convert, find the rectangular coordinates of the points whose polar coordinates are given below. Okay, so this should be an easy one because you know that pi/4 is 45 degrees, so you can sketch this out. Negative 45 degrees would put us here. Radius of 7 means that literally our radius is 7, so that becomes the hypotenuse of a right triangle. And you could use 45, 45, 90 right triangles. You know the hypotenuse is the leg multiplied by √2. So the leg then is 7 divided by root 2. And this one is also 7 divided by root 2. This one will be positive, but this one will be negative. So my coordinates will be, now if I rationalize my denominator, it'll be 7 root 2 over 2. And negative 7 root 2 over 2. I'm just going to leave it at that. I would say the best approach there is to just do it by geometry. It's easy enough if you know your special right triangles. For part B, you got this 240 degree angle. So that's 180, then another 60. So this is another special right triangle. You've got your 60 degree angle here, and you're being told that your hypotenuse is root 3. Well, you're supposed to know that the short leg is the hypotenuse divided by 2. So your x-coordinate then would be negative root 3 over 2. And you're supposed to know that your long leg is the short leg multiplied by root 3. So root 3 over 2 times root 3 would be normal 3 over 2. And of course we're going down, so it would still be negative. So those should be the coordinates there for part B, using just a purely geometric approach. Now for C, here's where we're not a special right triangle anymore, so geometry is not really going to help. But if I have an 80 degree rotation angle, then that's not really the angle I want. I want this angle. So if this was 80, then this is 80, which means that angle is 260. And it also means, of course, that the hypotenuse is 4 because they gave us a radius of 4. Alright, so how would I go about finding the legs of this right triangle? Well, it's just basic trigonometry. This horizontal leg would be the radius times the cosine of theta. So you know that your x-coordinate is going to be 4 cosine 260. And then your vertical component is going to be 4 sine 260. And that's it. You could literally give your answer like that. You're not going to even have a calculator, but pretending for a moment you did. Here we go. Pretending for a moment you did. Move that over. Then you could calculate this. You could go second quit. Oh, I can't control that. Second quit. You're going to go 4. Am I in the right mode? I'm not, because I'm using degrees. So degrees. Second quit. 4 cosine 260. Enter. 4 sine. Okay. How's that feel? Does that feel about right? I think it should. If you don't trust my drawing too much, then it should feel right. If you trust my drawing, don't, because that 80 degrees is, not accurate. We should have a much steeper angle at 80 degrees here. And then it would make sense that our x is quite small and that our y is pretty darn close to just the full value of our hypotenuse. So with our hypotenuse being 4, having that vertical edge at negative 3.939, that makes sense to me. And having our horizontal edge at only negative 0.695. That makes sense too. You should be expecting a short x with a long y relative to the hypotenuse. Alright, so that's how you can do that problem. You just use the formula. And that means this one is going to be basically the same deal. 5 pi over 12, that's in quadrant 1, because obviously if this is 0 and this is 12 pi over 12, because that's pi, this would be 6 pi over 12. And obviously 5 pi over 12 is going to pull up a little short of that. So you should have this angle in mind as you think this through. Now, this is a dumb one, because look at our radius. Our radius is 0. So we're just getting a point here. So what are we doing? Converting this to a rectangular? It would literally just be the point 0, 0. Which makes sense, because if we follow our little formula, then 0 times the cosine of anything, comma, 0 times the sine of anything, that's always going to be 0. So any polar coordinate that has a radius of 0 is, literally just modeling the origin, and that's all. So there. Let's move on. Alright, so we're converting the other way now. And hopefully an 8 and an 8 root 3 look familiar to you. Because if I go over 8 and down by 8 root 3, then I'm going over a little bit, down a bunch. And if this is 8 and this is 8 root 3, then that should be ringing bells in your head that this is a 30, 60, 90. With this angle as the 60, and the hypotenuse therefore at 16, because the hypotenuse is short leg doubled. So using just a little bit of geometry, we know that this represents the point with a 16 radius and a negative 60 degree rotation angle, so negative pi over 3. Other answers are possible, of course, because polar coordinates are not unique. But that's the answer that I'm given. So there. 10, 10. That's another easy one, quote unquote easy one. Because if I go left 10 and up 10, then you should certainly be recognizing that as a 45, 45, 90. Where the hypotenuse is 10 times root 2. And of course where the angles are 45. So that means without any muss or fuss, I can see the radius at 10 root 2. And I can see a rotation angle of 135 degrees, or if we want to stick to radians, which of course we do, that's just 3 pi over 4. Alright, what about 12/6? For 12/6, you're running over 12, you're running up 6. But that's not a special anything. So, it seems like instead, you're just going to have to do Pythagorean theorem. If you want this radius, well, you know that r squared equals the 12 squared plus the x squared. So 144 and 36, that makes 180. Yeah, and then clean that up. $180 can be divisible by what? Certainly a 9. That would leave us with 20. What have I done? Stupid. Not that stupid, but a little stupid. Alright, 9 and 20. Now 9's a perfect square, so I won't mess with it. 4 clearly has a perfect square factor here, and 5 is a prime factor. So 9 and 36, you can put them back together and just call that 36. What did I just say? 9 and 4, you can multiply them together and you'd see that you get 36. So we can see that 180 is 36 as a prime perfect square factor, and 5 is a prime factor. So 180 is 6 root 5. Yeah, I do want you to be able to do that. So this radius should really be 6 root 5. What's the angle here? Well, I don't know, but I bet inverse theta does. Oh man, am I tired? I must be tired or something. Inverse tangent of theta. No, that's not even right either. Theta equals inverse tangent of 6 over 12. So what could that be? $26.565. But again, you're not going to have a calculator, so I guess you'll just know that this is your angle, because we're in quadrant 1. And so even though that's technically phi, the rule in quadrant 1 is that theta is phi. You don't have to mess with it at all. So I don't know, but the best way to write these coordinates, and I've run out of space, so let me make more space. Okay, the best answer, I guess, is to say the radius, which is 6 root 5. And then give the angle as this inverse tangent expression. Not as 6 over 12 though, 1/2. So now you've got your radius covered and your angles covered, but you're giving the angle exact instead of rounded off. Again, you're not going to have a calculator, so you won't be able to give me the 26, which I'm realizing was completely in the way as I tried to do part B. Oh, hello. Hey. Okay, I'm back, I think. I hope. -3, -8. Do the same thing you did for the other one. Sketch it out. -3, -8 means left a little, down a bunch. So find that radius. If I haven't explained this already, we're basically doing the same thing we did with vectors, right? The radius of our point is like the magnitude of our vector. So you know the radius is just going to be the -3 squared plus the -8 squared. Which means, well, it's the square root of that, of course. So that's 9 and 64, so 73. And then the angle again, if that angle is phi, then we want 180 plus phi. So you could just give your answer as root 73, that's your radius. And your angle would be, I guess we'll say pi plus the inverse tangent of 8/3. And technically it has to be the absolute value, or else you're not quite doing it right. That's it. I don't feel like getting too deep into that one, but there it is. Next. Alright, so now we're converting each rectangular equation below to polar form. Alright, fine. So, you should hopefully remember that we had three little rules, three major rules. R squared equals x squared plus y squared. And x is r cosine theta. And y is r sine theta. So given that, we should be able to do any conversion. X, well, that's r cosine theta. And it equals -16. Typically you want to solve for r when you can, so we'll divide by 16. That'll give us -16 over cosine, but rather than saying over cosine, we'll just say times secant. And hopefully you've studied enough by now to know that this equation is the equation of a line, specifically a horizontal line located at x equals -16. So it should actually make perfect sense to you that these two equations are equivalent, because you should know this is a horizontal line, this is a horizontal line. Next, for this one, I guess we just make those same substitutions. We'll say r sine theta for y equals 3 cosine theta. And again, you typically want to solve for r, so divide by sine. And you get r equals 3 cotangent theta? Alright, I guess. Sure, sounds fine. Alright, and then lastly, excuse me, so this guy, yeah, I think we just want to do our mostly direct substitutions. Factor out a 2, and then you've got x squared plus y squared, so that can just become an r squared. And then your minus x is a r cosine theta. And your plus y is an r sine theta. Excuse me, that equals 0. Now what? Not entirely sure how to clean this up nicely. I'm going to say factor out an r. Sure. So factoring out an r, you'd have 2r minus cosine plus sine. Then if you stop and think about it for a second, if you think of this as a separate equation, then this thing for r equals 0, usually you can just get rid of that, because usually you get that same answer here anyway. Let's see if that's true. If r is 0, are we still going to get whatever? I don't know. I can't exactly justify that to myself, but typically that r, you can just divide it away. So divide it away. Then what? I usually do want to isolate r, so let's add the cosine, subtract the sine, and then let's divide by 2. So we'd get what? Cosine theta minus sine theta, and then just all over 2. And I don't hate that as a final answer. I think that's fine. So sure. Do I care enough to talk about this? I do. We'll talk about it the tiniest bit. If you look at this, you've got two quadratic terms that have the same coefficient. So that's pretty strong, and they're being added. So that's a strong indicator that this is just a circle. If you wanted to, you could complete the square to try to find out more information about this circle. But I don't want to do that, and especially when not with a 2. The leading coefficient makes completing the square a little bit harder. So I'm not going to go into depth about this. If you guys were really wanted to see the relationship between this equation here and the given equation, you could graph them both in Desmos and kind of look for those connections. It's not that important. I'm going to move on. Number 6. Okay, so 6a. This is a bit of a weird one. None of our little conversion factors work because we just have theta. But think this through with me. Theta equals a number. That's just a line. And so if you imagine 7 pi over 6, that's 6 pi over 6 plus another pi over 6. That's a 30-degree angle. And of course it passes through the origin. And so you're just talking about a line here. And so you know its equation will be y equals mx plus b. Running out of space here. But since we pass through the origin, you know that b will be 0, so you're just talking about y equals mx. So if you stop for a second and think about tangent, the tangent of an angle is what? Y over x, opposite over adjacent. It's the rise over the run. So you can think about the slope of a line as being the tangent of the angle that that line forms with the x-axis. So for us, that given angle is that angle. And so for us, that slope is that tangent. So you can just kind of rest assured that any polar equation of this form will just turn into y equals, instead of mx, it'll be tangent of 7 pi over 6 times x. I would not want you to leave it like this, because tangent of 7 pi over 6 is an expression you're supposed to know the value of. So 7 pi over 6 puts us here. 1 pi over 6 had coordinates of root 3 over 2, and then 1/2. So over here in quadrant 3, our coordinates would be negative root 3 over 2, comma, negative 1/2. And tangent is, like we said, the y over the x. So it would be the negative 1/2 over the negative root 3 over 2. So kill the 2's, kill the negatives, you get 1 over root 3, which is really root 3 over 3. So plugging back in, you could give me y is equal to x root 3 over 3. And that's a pretty nice way to express that equation. You've got the slope, everything's good to go. Okay, next. For this one, I like this one. This one's not quite right. Is it? All right, I'm getting close to that 30-minute mark where my software likes to cut out and just end the video. So if I get cut off, forgive me. Hopefully that won't happen. I did update it to the latest version, so maybe we're fine now. But anyway, so to do this, what do we see? Remember, our rule is that r cosine theta equals x, but this is r secant theta. That's r over cosine theta. So you can't just do a direct substitution for that, but you could multiply both sides by cosine. Then you get r equals 5 cosine theta. And that probably doesn't seem like much of a help because 5 cosine theta isn't anything. We need r cosine theta. But that's when you realize that multiplying through by r to give you r squared equals 5r cosine theta, that's a helpful move. So now we can say that the r squared is an x squared plus a y squared. We can say that this is 5x. Now we're in a position to recognize that this is a circle, and we can put it in the right form by completing the square. So we're going to go x squared minus the 5x, and we're going to leave some space to complete the square with. We've got the plus y squared, which thankfully is already in completed square form. It doesn't have a linear term of y, it just has y squared, so we're fine in that regard. Now we're going to have to add something ugly because we want half of 5 squared. So 5 over 2 squared will be 25 over 4. Not the ugliest number in the world, so it's not like you should be that mad about it. But it's definitely 25 over 4 is what we're adding to both sides. And that's going to give us a factorable trinomial. It's going to be x minus 5 over 2. All squared. We'll add to that y squared. We'll set that equal to 25 over 4, and then you're done. And just as a reminder, you are supposed to understand the connection between this and this. You're supposed to remember that, well, you're probably supposed to remember it from here, where we had r equals 5 cosine theta. You're supposed to remember that as a circle, that maybe it started at the origin, but somebody translated it over so that it's now tangent to the y-axis, passing through the origin. Instead of being centered at the origin, it passes through the origin. And its diameter is 5. So you'd get a point at 5, you'd get a point at 0. Your center would therefore be 2.5, and you're talking about this circle. And of course, once you put yourself into the standard form, you can see that's true. We see our x-coordinate at 5 halves. For our center, our y-coordinate is at 0. Our radius will of course be the square root of this number, so 5 over 2, which does mean a diameter of 5. So this form, this rectangular form and this polar form, they do line up perfectly. Okay, so C is now the same exact deal. C is like the easier version of B, because for part B you had to do the legwork to get to this step and then realize you could multiply through by r. Here you're already there, so we can see here, hopefully, that we just want to multiply through by r again, and we would get 4r sine theta, which is 4y. That equals r squared, which becomes x squared plus y squared. So again, we just want to subtract and complete the square, so we get 0 equals x squared, which we don't have to worry about, then y squared minus 4y, and here's where we need a nice big space to complete the square with, so we'll just add 4. To both sides, and we'll get 4 equals x squared plus y minus 2 all squared. And that's it. So again, we see a center at 2, 0, no, super psych, 0, 2. And we see a radius of 2, which again means, I know that I'm kind of behind my face, but I don't care. We go up 2 to find our center. We've got that diameter of 4, so we've got a max up here at 4, and we're just getting a circle centered here on the y-axis, translated sort of up, and that's because it's sine this time instead of cosine. But that's it for the graphing problems, but not really, right? No, There's more graph. That's it for the converting. I would say that if you only did these converting problems, that would definitely not be enough. So you better do some of the converting problems from the homework too, because these few problems aren't going to cut it for the quiz. There's harder ones on there for sure. Moving on. All right, graph the polar equations given below. These two are super easy. A radius of -9/2. That just means a radius of -4.5. And if there's no theta, then you can just be anywhere as long as your radius is 4.5. So 1, 2, 3, 4.5 gives you a point there. Literally any point anywhere. 4.5, 4.5. You could be at 4.5 at 45 degrees. You could be at 4.5 at -60 degrees. But hopefully it's obvious that what we're getting is a circle whose radius is 4.5. The values of theta don't matter. So that's it. You just draw a circle, centered at the origin. This guy, theta equals -200. Well, where's -200? Right here. 10, so more like 2/3 of the way through. But that's it. Just like when r is some number and theta is not associated, if theta is some number and there's no r associated, then as long as you're on the line that forms the correct angle, then you've got the right graph. So we can let the radius be anything. So we're just getting a straight line like that. The only interesting thing I saw as I looked back through a few problems was there were times in the past when I gave like theta, I think I said theta squared equals 900. And so from there you had to know that if you took the square root of both sides, you would get theta equals plus or minus 30 degrees. So what would that be if you graphed that? That would actually be two intersecting lines, right? Notice I'm talking about something else. If your attention lapsed, I'm explaining what a slightly different kind of equation might look like. If you had theta squared, forget this, equals 900, then you get two lines. You'd get one for positive 30, which just goes running that way. But technically there'd be another line for -30. And so your graph would be two intersecting lines forming 30-degree angles with the x-axis. So that's slightly more interesting. But moving on, the next four are our good limacons and roses. So if you're confused on those, here we go. Okay, so to graph these, it would be awesome if you could just do it from your head, I suppose. But if you're not sure what this is going to look like, then what you probably want to do is sketch the associated sinusoid. And then from the sinusoid, you can pull out ordered pairs that you can plot in the polar grid to give yourself a better sense. Again, you should probably know, I'm going to do this just super roughly at first, that this 2 is our midline. So you should be expecting to go up 2 and have a midline there. Then you're graphing a negative sine function with an amplitude of 5. So that means from 2, we'll go up to achieve a max at 7. But we'll run down to achieve a min at -3. And for a negative sine function, we'll start at our midline, but from there we'll run down to our min. You know what? That wasn't that rough. That's fine. Take this grid, honestly, and shove it. We don't need it. A rough sketch is perfect. I mean, this is great. Oops, why can't I grab it? Grab. Move. Okay, so the thing is, just make sure you remember, there were no b values, meaning our period was unchanged, right? It was just theta, not 2 theta, 4 theta, whatever. So you know the end of the line over here is that full 360 rotation. This midline point is at 180. This min is happening at 90. This max is happening at 270. So again, pull out those ordered pairs and plot them. At 0, we're getting a radius of 2. So go out to 2. Bonk. At 90, we're getting a radius of -3. So at 90, -3 means don't go up, but go down. 1, 2, 3. Then at 180, you're getting 2. So at 180, you're getting 2, go over 2. And at 270, you're getting 7. So at 270, go 1, 2, 3, 4, 5, 6. Annoying, go out to 7. So a little further than the grid. And finally at 360, you get 2, which of course has us back here. So this is a limousin with an inner loop, which of course we knew, because when the bulk of our graph has one sign, like most of it's positive, but there's a little bit that's negative, that little negative bit's going to force that inner loop. Same thing would happen if you had a graph that was largely negative, but every once in a while was positive. Right? This graph here would also be cardioid with an inner loop. Limousin with an inner loop, not a cardioid. Anyway, to sketch this thing, I'm still going to be kind of a pain in the butt about you guys actually sketching it well. So, I don't know, a couple ways to think about this. Remember, it should be largely circular, so picture a circle. And down here at this min, you should see basically a circle that's flattening out. This needs to be like a lot bigger. But yeah, I mean, as you hit that bottom point, you want to be coming into that point pretty horizontal. Your curvature away from it should be pretty slow and gradual. If you turn away too quickly, that's when you get your way too skinny shape. So here's a circle. You can kind of keep that as a benchmark. The other thing to think about is if you actually were to imagine like a rectangle that went through all these points, like this, you know that you should actually have a shape that bulges out beyond the left and right sides of this rectangle. Your shape should bulge up above the top of this rectangle. So if you take those benchmarks into account, that should help too. So what did I just say? We want to be pretty gradual as we move away from this point. And we definitely want to come out and around this rectangle. Oh, this isn't good at all. Yeah, I don't love that. That's okay. Here we should be hitting at the pole, but I do come up above and then I loop around. Here I come up above and I loop around. If you drew that, I'd hate it, but it's not the worst thing I've ever seen. But for sure I would say this thing should bulge out more. Maybe that's a little bit better. Anyway, just try to do your best with it. But that's our shape. The main thing to understand, of course, is how the sinusoid relates to the polar graph. Okay, moving on. All right, this one. What's this? Well, the last one actually had sort of a D value, so to speak, right? So if I was to rewrite this, it would be -5 as an A value. No B value, no C value, but then a +2 as a D value. So this had that classic limousin form, but the next one doesn't. This one has an A value and a B value. So you should hopefully be recognizing this as a rose. Exclamation point. You should notice that because that coefficient, that B value is 3, that's odd. So the number of petals is actually 3. And this is hard to explain and I'll probably screw it up. But basically, if you know how many petals you got, the next thing to figure out is where do those petals fall. If this was a cosine function, then you know that one of your petals just always starts out symmetric on the x-axis. Just kidding. If it was negative cosine, you'd have a petal that started out over here on the negative half. But then from there, you just kind of spread them out symmetrically. Like you'd know that if there was supposed to be 3 of them, then they'd be 120 degrees apart. So if you knew that you had one over here on the negative x-axis, you'd know the other one was 120 degrees later. So at pi/3, you'd know the other one was here at 5 pi/3. And then you could just kind of rough it in and go, oops, that was actually atrocious. You'd go around and around that one, down there, and then back home again. And you'd have your 3 leaves, right? Sine's different. Sine doesn't work like that. Clear annotations. Yeah, clear annotations. Do it.